Okay, we're going to talk about problem 17 of midterm 2, and the question asks, a particle with charge q moves through a uniform magnetic field with velocity v equals v naught I hat and feels a force of F equals F naught over the root 2 times j hat minus k hat. And they would like to know, what is the magnitude of the magnetic field? Here's the explanation to the problem. The magnitude of the magnetic field is going to equal the square root of bx squared plus by squared plus bz squared. And we know the velocity is equal to v naught I hat. Here are a couple cross products that are going to come in handy during this problem. I hat cross j hat equals k hat cross I hat equals j hat, and j hat cross k hat equals I hat. We also need to know that the force is equal to the charge times the cross product of the velocity and the magnetic field, V cross B. It is given to us in the problem that the force is equal to F naught divided by the square root of 2 times j hat minus k hat. And from this equation above, we know that the force over here is equal to the charge times the velocity, which was given to us as V naught I hat, times the cross product of the magnetic field, which, since we're trying to find the different components so we can find the magnitude, we're going to label as bx I hat plus by j hat plus bz k hat. So next step, we're going to distribute the cross product, and we're going to get q times v naught times the quantity of bx I hat cross I hat plus by I hat cross j hat plus bz I hat cross k hat. And now this term here is going to be 0 because there's not enough information given to us in the problem to figure out what it is. And then any term we find, the magnitude of the magnetic field is going to be either greater than or equal to the term we calculated in this problem, because we can't calculate this x term. So from there, we will take the cross products, and we know from up above that I hat cross j hat is going to equal k hat right here. And then I hat cross k hat cross I hat is going to equal j hat. So because it's the opposite, it's going to be a negative j hat. So that's how we get this term here, negative bz j hat. And then after that, we know that our force, this force, is equal to the charge q times v naught times the quantity of by k hat minus bz j hat. From there, we can set the k and j terms equal to each other and solve for the components of the magnetic field. So F naught over the square root of 2 j hat from this equation up above is going to equal negative q v naught bz j hat, this here. And we can solve for bz, and we get that bz is equal to negative F naught divided by the quantity of square root 2 times q times v naught. Now we can do the same thing for by, set all the k terms equal to each other, and we're going to get negative F naught over the square root of 2 k hat is equal to q v naught by k hat. So we solve for the magnetic field in the y component, and we get that by is equal to negative F naught over the square root 2 q times v naught. From there, we find the magnitude of the magnetic field by squaring all the components of the magnetic field. So we're going to square the bz term, get F naught squared over the square root of 2 q squared v naught squared, plus square the by term, F naught squared over 2 q squared v naught squared. And since the bx term is 0, we can ignore that. You add these two terms together and take the square root, and you're going to get that the magnitude of the electric field is greater than or equal to F naught divided by the q v naught.